So, hello everyone. It's very nice to be with you here today in sunny California. So, as Jan mentioned, I'm Raphaël Douin, a solution engineer at DDN and based in France. So, I look after our AI Frontend X2 product, which is a turnkey exascaler-based storage system that's fully optimized for AI and HPC workload running on GPUs. My team and I also work very closely with AI compute and software manufacturer to integrate the AI Frontend X2 as part of complete AI infrastructure solutions. For example, NVIDIA SuperPods, which we have heard about at previous Lustre community meetings. DDN has been very successful in deploying Exascaler with customers pursuing AI globally, and we have gained a tremendous amount of experience and expertise along the way. So over the next 25 minutes, I would like to share with you some of our recent work related to training AI at scale. Particularly, I would like to talk about how our use of local caching in client nodes helps increase the pace and the efficiency of training AI models. So this is a quick overview, and I hope you will find some of those examples interesting. If you would like to engage more, please connect with me at the conference or drop me a line at my email. So first, I would like to take a moment and tell you about the data platform that my colleague and I have developed. So training AI at scale with deep learning techniques requires a tremendous amount of data and computing power. So we have to deliver exceptional amounts of performance, scalability, and reliability to ensure that AI workflow operates optimally. Lustre and Exascaler are obviously quite well suited to meet this need. This is not new for those of you who have been in HPC for a long time. But with AI customers, we have to bring all the goodness and capabilities of the file system in a simple package that it's easy to deploy, manage, scale, and support. And we have to provide a product that enterprise IT staff or even cloud-native programmers can operate seamlessly. So we've designed this AI Frontend X2 appliance, which is really an AI data storage building block. It's a turnkey all-NVMe appliance. It has fixed hardware and software configuration. It arrives ready to deploy. Customer hooks it up to their InfiniBand or Ethernet network and can start reading and writing file and achieve a very predictable level of performance. So there is no tuning needed, and we've placed default setting that satisfy nearly all of our customers. To give you a sense, we have nearly 1,000 of these appliances deployed globally. The simplicity of the package has been the key to driving the Exascaler adoption in the AI space. So the AI Frontend X2 appliance delivers up to 90 gigabits read, 65 gigabits write throughput, and around 3 million IOPS random readouts out of the box. So it does this constantly and again out of the box. We deliver a determined amount of performance, capacity, and capability with each appliance. So everything is contained in a single appliance: data, metadata, MGS, and obviously the storage scale linearly as you increase the number of appliances. So this simplicity is largely driven by software enhancement within the appliance itself, including the file system. One of the major developments we have introduced to Exascaler to help make the appliance more accessible for customer is EMF, the Exascaler Management Framework. Joe Grant on our team is leading the project. So it's a software stack that allows us to deploy, configure, and monitor and upgrade appliances through a centralized facility. So it provides CLI, API, GUI through which customer can take the appliance from first boot through production without having to deal with complexity of managing all the individual components of the storage system. So with EMF, we replace our traditional text files, manual processes, local client and server configuration with a single centralized facility. That really helps simplify access to the file system and also help accelerate operation and provide better resiliency and visibility into the cluster. So EMF is a very good example of a feature we developed out of a need from the AI customers. And that's had a very good, very positive impact on exascaler file system adoption. So everyone benefits from this. So we work very closely with AI compute and software manufacturers, including NVIDIA. Of course, there are others, Intel, Habana, AMD, Cerebras, GraphCore, to name a few. But NVIDIA is by far our largest partner and customer. So as a DDN customer, NVIDIA operates hundreds of our AR400X2 appliance to power their internal AI infrastructure. So in the slide shown, it's Celine, which has close to 4,500 GPUs connected to 40 of our data platforms. So it gives you about 15 petabytes of NVMe capacity, 2 terabytes of read throughput, and 1.4 terabyte of write throughput. So we are currently working on the storage system for the next generation SuperPod, which we expect will double the performance and also capability to meet the needs of new generation H100 GPUs. So this story is really about ready to deploy AI supercomputers. NVIDIA has packaged compute and network building blocks, and our data storage appliances fit nicely in that story. So today we provide storage for over 5,000 DGX systems worldwide at NVIDIA and with joint customer globally. Some of these deployments are at massive scale, like Celine. Some other are like single compute and storage, and everything in between. So again, the way we've packaged the technology and the shared parallel file system make a huge difference for workload on GPU and AI application. So I don't have time to go into the details, but really is massive parallelism in the architecture, and all the goodness around data management security are very beneficial for this market. So anecdotally, we used EMF for deployment on a very large SuperPod recently. So we deployed 48 of those AR400X2 appliances from box to production in less than a day and clocked full performance from the clients. So here is another example of that. So we took 12 AR400X2 appliances, joined them in a single file system, and connected 20 DGX A100 compute clients and achieved nearly full line rate out of the box. So every DGX client can achieve roughly 45 gigabits read and write throughput using the two HDR200 IB links. We ran synthetic performance tests and achieved full perf and nearly linear scaling without much effort. This really speaks to the simplicity story. And it's enabled by the architecture and advancement in the file system. But it's also the way that we have packaged it. So this graph also speaks to the accessibility component. With the building block approach, it makes it simple for customer to architect data platform with reliable prediction and for capacity and performance. So customer really appreciate the simplicity and confidence that they will get what they expect from the file system. Also, the ability to deploy the system very rapidly and without the need for in-depth expertise or engineering. I'm sure some of you can relate to that. So traditionally, projects like this can take months and require a lot of experts, risk, and surprises. But with the AR400X2 building block enhancements like EMF, we can deploy those very large, powerful file systems in a matter of hours using standardized procedures. So that's really important for AI customers since they are deploying powerful compute infrastructures, sometimes at very large scale. So they need to achieve full performance out of the box, and they may not have the in-depth expertise to achieve this. Oftentimes it's a race for time and to go to market. So the building block philosophy has been a very important part of our success in the mainstream AI market. So let's now focus more on the topic of this presentation. So we'll focus on NLP workload, natural language processing, and more specifically large language models such as ChatGPT, also known as GPT-4, that I'm sure you all heard of, and how we can maximize the training efficiency using data caching. So as you all know, the size of AI models has been growing rapidly in the recent years. So in order to train those large models, we need to use distributed training methods that utilize hundreds or even thousands of GPUs. So this allows us to break the data into smaller pieces and train the model more efficiently. With the increase in model size, we also need larger and more complex data sets to train them effectively. In fact, these data sets are often multiple petabytes in size and costs are constantly growing as new data is added. So to train those large modules, we need to read data from disk very quickly. So the primary I/O pattern we see is small random reads, which can be very challenging for traditional storage system. So to address this challenge of small random reads I/O pattern, many AI applications use the mmap POSIX function to load data into memory, and a lot of improvements has been done in this area in the last few years, thanks to you and the community. So with the rise of containerization, AI applications are deployed in more complex environments. This requires new data path optimization to ensure that the data can be accessed quickly and efficiently from within the container and ensures its integration with common container software. So during the training process, it's important to minimize the impact of failure. So to achieve this, we use checkpoints, which allow us to save the model states at certain point during the training. And if a failure occurs, we can simply resume the training from the last checkpoint rather than starting over from the beginning. So as GPU systems become more powerful and AI models continue to grow in size, we can expect to see a steady increase in data volumes and I/O performance over time. This will require us to continue to optimize our data caching and storage system to keep up with the demands of AI training. So let's dive a bit more into the importance of checkpoints in training long-running AI model efficiently, especially at scale. So checkpoints are an essential tools that allow us to register, save, pause, and resume AI application, among other things. So checkpoint take a snapshot of a model and store it in a non-volatile memory. So this allows us to pause and resume tuning at a particular step in the process and recover from any failure with all progress, and most importantly, the energy used is saved. So checkpoints are crucial in improving inference prediction accuracy. So when you do continuous learning, you take your intermediate models, which are usually deployed for inference, while online training continues with new data sets and parameters. So checkpoints also allow us to relocate AI processes to a different system. So this makes it easy to migrate to another platform, which is ideal in case of infrastructure faults. Finally, checkpoints are also used for non-disaster recovery scenario and is part of the common AI workflow to allow us to perform transfer learning. So intermediate model states can be used as seeds to train for a different goal. So this makes the process more efficient and reduces the amount of training time needed to achieve the desired outcome. So as we saw, the size of data sets in AI training is growing rapidly, so which poses a significant challenge for distributed training scenarios. One of the main challenges is the limited capacity of worker memory. Which can result in the need for continuous reading of the dataset from shared storage during the training process. So this continuous reading of data from shared storage can cause a significant load on the storage system and impact the performance of other I/O-intensive tasks. For example, so if the storage is busy reading data for AI training, it cannot be used at its full potential for the tasks, such as performing checkpoints, ingesting new data, or handling any other cluster activities. This can lead to delays and slow down the overall training process, resulting in increased cost and decreased efficiency. So to address this challenge, local cache can be employed. So in this scenario, each worker node maintains a local cache of the data set, which is used for training. So instead of continuous reading from shared storage, this local cache is automatically updated from shared storage, reducing the load on it. and freeing up resources for other IO-intensive tasks. So using local cache can significantly improve the efficiency of the distributed training scenarios, as workers can train on datasets without the need for continuous access to shared storage. So this can result in faster training times, reduce costs, and increase efficiency of the whole workflow. So we can leverage this local cache thanks to odd nodes, which is based on the Lustre PCC feature. And this can significantly improve the performance of AI applications by caching data on local NVMe devices in the client. So this solution eliminates the need for manual data management overhead, which can be risky and time-consuming. So instead, automated data movement from shared space to local nodes with intelligent policy-based cache management makes the process entirely transparent for users. So this is an automated approach that ensures that data is efficiently managed, freeing up resources for the task and reducing the burden on shared storage. By leveraging local cache, significant efficiency and AI workload improvement can be achieved, especially for at-scale NLP. This is particularly important when a large number of nodes are engaged simultaneously for training. With the use of local cache, each node can access data it needs for training without putting a significant load on shared storage. So another benefit of using local flash for AI training is a reduced latency in accessing data. With local flash, data can be accessed at a lower latency than if it were storage in a shared storage across the network. So this can result in significant performance improvement. So cache management is an essential component for efficient AI training, and there are several tools available to help us manage data caching. With these tools, we can have fine control over the cache behavior, implement policy-based cache management. So one of the key benefits of the tool is the ability to monitor cache utilization and its statistics. So this helps us understand how effectively our cache is being used and identify areas where improvement can be made. The other interesting advantages is the ability to integrate with MLOps platforms such as NVIDIA-based Command. So this allows us to manage caching from a single interface, to be able, for example, to pre-flight load data. By loading data in advance, we can reduce the need for workers to read from the shared storage, improving the overall training efficiency. So now let's see a visual representation of all an AI workflow and review the advantages of what nodes. So in the video you will see, so at the bottom it's 20 DGX systems, and on top it's 12 AI Phone X2 boxes. On the left on the screen shows the read throughput, and on the right is the write throughput. So we first read the dataset from the shared storage. As it can fit in worker memory, the dataset is continuously read from it. So this keeps the shared storage system under a constant load, which impacts the other operation as happening as part of the pipeline. So now, with the help of odd nodes, we can leverage local drive as cache. As the dataset is read during the first training epoch, data are cached on each node automatically. So we can see the cache is filling up, and once the cache is completely filled, the training can continue using the cache and freeing up the storage system. So during every subsequent epoch, data is read seamlessly from the local cache. After some time, the model is checkpointed, so we can see some write throughput happening to the shared storage. And now we'll resume the training on a subset of the node and start a new training on the other set. So the top row continue training. The node flush at the bottom flush the cache automatically and start reading the new data set to train the model. So after some time, the first set of nodes finished training in a bit. And now we can checkpoint the model at maximum rate, since there is no continuous read from the other in-training sets, as the data is cached locally thanks to odd nodes. So OddNodes is currently used today in production environment to power one of the largest AI supercomputers in the world and to make the distributed training process more efficient, as shown in the previous slides. So the DDN's shared storage is not only used for reading the dataset, but also for other activities. The shared storage remains available for other IO-intensive tasks when it is not being used for AI training, making it a highly efficient solution for large-scale training. OddNodes showed improvement for the megahertz GPT-3 model back in 2020. So today's models are 40 to 50 times larger. If you are a bit more interested in more detail for this specific use case on the Selene SuperPod, I invite you to review the Accelerating AI at Scale with Selene Digix A100 SuperPod and Lusterpile 5 system storage presentation done at LUG 2021 by Prithvi Kashingunti and Julie Bernauer from NVIDIA. So now let's see a bit more about what features are really suited for AI workflow. So as we saw, the size of data sets in AI training is growing rapidly, and with the storage needs to store them. So we will introduce later this year a new expansion enclosure to easily and seamlessly add high-density QLC flash to the AR400X2 solution. So QLC drives will allow you to increase your flash storage at a cheaper cost compared to TLC flash while maintaining flash performances. So this enclosure will rely on a switchless NVMe over Fabric technology to enable connectivity between the head nodes and the expansion enclosure with no single point of failure. So this new enclosure features a real-time many-core red engine that is capable of driving QLC flash at the highest speed possible. This provides exceptional performance for even the most demanding workloads. With the ability to support up to 7 petabytes of QLC flash in just 10 AU, this appliance offers an unprecedented level of storage density. And thanks to its zero mid-plane design, this new enclosure has no single point of failure. This ensures maximum uptime and reliability even in the event of component failures. So with no external switching required, the appliance offers simple scale-up and scale-out capabilities, making it easy to expand your storage capabilities as your organization grows. The other interesting feature is the CSI driver, which is particularly important for MLOps platform running on Kubernetes. So in MLOps, data is a critical asset, and security is of importance to ensure confidentiality, integrity, and availability of the dataset throughout the machine learning pipeline. So Kubernetes is widely used in MLOps platform to manage and orchestrate containerized workloads. So with the DDN CSI driver, MLOps platform can leverage the security feature of Kubernetes to protect data, while also benefiting from the flexibility and performance of containerized workloads. By enabling per-tenant authentication and access controls, central volume management, and fine-grained quota administrations, the DDN CSI driver can help MLOps platform ensure that only authorized users can access and manage their storage volume. This also helps to prevent unauthorized access or tampering with data. Additionally, the dynamic publish and unpublish feature provided by the CSI driver can help MLOps platform manage the lifecycle of storage volumes, creating and deleting them as needed to support the dynamic nature of the machine learning pipeline. So overall, the DDN CSI driver provides a secure and flexible storage solution for MLOps platform running on Kubernetes. And it enables organizations to securely manage their machine learning workload at scale while ensuring that their data remain protected. So if you are a bit more interested in the work we did with my colleague and I, you can review some of the reference architecture at this link, and you can I invite you to review the talk done by Prithvi and Julie from NVIDIA in 2021. So again, thank you for your attention. I hope that you enjoy the session. My colleague and I are here. Please connect if you would like to chat some more. I would love to hear about what you are doing with AI and HPC workloads on GPUs. And on a personal note, I would like to thank you all for contributing to the development of an amazing piece of technology, and also for being such a vibrant and welcoming community. It's been very fulfilling experience working within the Lustre community over the last 3 years, and really grateful to be part of this group. Thank you.
Do we have any questions for Raphael?
So going back to the, what was it, EMF?
Yes.
So I'm picturing like a truck shows up with a bunch of DDN stuff on pallets. I wheel that in my data center. What work needs to be done between like wiring everything up and EMF giving me a Lustre file system? Like where does EMF start in that process?
So EMF starts as soon as you are able to access the appliances. So you first need to, for example, set IPs just to be able to SSH them. And then using EMF, it will deploy the entire file system. So within EMF, you can configure the number of OST, MDT, any tuning or MKFS tuning you would like to apply. And it will automatically deploy the whole file system. So if you are a bit more interested in EMF, there is a demo on ddn.com website that shows a complete installation within 15 minutes.
Thank you. Any other questions? If not, we'd like to thank Raphael very much for his time and his presentation today, and we will continue with our program.